Welcome to this introductory video for Module 5B. As usual, we start by reviewing an engineering disaster. The Bangqiao Dam was located in Henan, China. Construction was completed in 1953, but so-called reinforcement efforts were added from 1955 to 1956. Soviet engineers provided structural direction to the Chinese government. The Bangqiao Dam was nicknamed the Iron Dam to reflect its seeming invincibility. Construction projects such as this one were characterized as part of the Great Leap Forward, a modernization plan by the Chinese Communist Party to transform China from a mainly agrarian society into an industrialized juggernaut. Chen Xing was the chief engineer of the dam projects and pointed out that the local geographical conditions made it unreasonable to overly emphasize the reservoir's function of water storage because otherwise there was risk of creating serious floods and other disasters. His warnings were ignored, and he was criticized for not supporting the government and was finally removed from his post. In 1975, Typhoon Nina hit Taiwan and then moved up through mainland China toward the Henan province. The Bangqiao Dam had been designed to withstand a rainfall event of 300 millimeters per day. However, more than 1,060 millimeters fell in just one day near the typhoon center. When the dam's wave wall finally collapsed, 701 million cubic meters of water was released over a period of 6 hours. The official death toll for this failure was 26,000 lives lost, although some estimates indicate this number could be up to 10 times higher, given that the Chinese government attempted to cover up the magnitude of this disaster. The primary method for analyzing brittle materials is the modified Moore theorem. This theorem is an adaptation of the Coulomb-Moore theorem, incorporating additional factors like the influence of the intermediate principal stress, as well as nonlinear behavior, making it better suited for complex stress states in materials like rock or concrete. Since brittle materials show little to no yielding prior to fracture, the material's ultimate strength is used as the limiting design factor. Remember, brittle materials have less than 5% elongation at break. For the modified Moore theorem, we need to calculate the three principal stresses and the three Dowling expressions defined as C1, C2, and C3. The highest of these six stresses is compared to the ultimate strength to determine the factor of safety. Remember, brittle materials fracture rather than yield. In tension, they fail due to the normal tensile stress alone, whereas in compression, they fail due to a combination of normal compressive stress and shear stress. Also be cognizant that brittle materials are known as uneven. This means that their compressive strengths are significantly different, usually higher than their tensile strength. In general, brittle materials are used when an application has significantly high compressive loads. However, many applications see both tensile and compressive loads, requiring the engineer to select the best option from either ductile or brittle materials. An interesting property of brittle materials is that when under compressive load, their shear strength actually increases. We will consider three brittle failure theorems: maximum normal stress, Coulomb-Moore, and modified Moore. By now, hopefully we are getting used to seeing the stress envelope diagrams. Just as we did with ductile materials, we will also overlay the brittle material theorems on the same diagram. Just as when we looked at ductile materials, we start with the most basic theorem, the maximum normal stress theorem. This assumes that when the principal stress equals the yield strength, then failure occurs. Remember, the shaded area of the rectangle is considered the safe design zone, and the areas outside of the rectangle are considered unsafe. Also recall that experimental testing shows that the maximum normal stress theorem is inaccurate for the second and fourth quadrants of the diagram. And by way of review, recall that the maximum shear stress theorem attempts to rectify issues with the maximum normal stress theorem by defining failure to occur when the difference between the maximum and minimum principal stresses equals the yield strength. While safer from a design perspective, it is somewhat overly conservative. The von Mises stress theorem is a further refinement of the maximum shear stress theorem. It uses the energy developed by the geometric distortion of the machine member compared to the yield strength to define failure. Experimental data supports the use of the von Mises stress theorem for ductile materials. However, this theorem is not accurate for brittle materials. The next refinement of the maximum normal stress theorem for brittle material is known as the Coulomb-Moore theorem. It is also known as the internal friction theorem. The maximum normal stress theorem compares the maximum principal stress to the ultimate tensile strength and the minimum principal stress to the ultimate compressive strength. Failure is predicted to occur when the combination of the maximum and minimum principal stresses exceed their respective stress limits. This can be related to Moore's circle, and that failure occurs when the graph of Moore's circle reaches the failure zones as defined by the ultimate tensile strength and the ultimate compressive strength. Note the formula for the Coulomb-Moore theorem: sigma 1 divided by the ultimate tensile strength minus sigma 3 divided by the ultimate compressive strength must be less than or equal to 1 in order for the design to be considered safe. The upper image shows the concept of Moore's circle contacting the failure zones, whereas the lower image shows the stress envelope diagram for the Coulomb-Moore theorem. Finally, we arrive at the modified Moore failure theorem for brittle materials. Note the stress envelope diagram that shows the Coulomb-Moore theorem in comparison to the modified Moore theorem. Another important consideration is that of hydrostatic stress. In the case of solid brittle materials, hydrostatic stress is the average of the three normal stress components, sigma 1, sigma 2, and sigma 3. For brittle materials, the hydrostatic stress can significantly impact the failure behavior, often fracturing due to the presence of flaws or cracks. Brittle materials, unlike ductile ones, are significantly affected by the overall state of stress, meaning that a compressive hydrostatic stress can significantly increase their resistance to failure, while a tensile hydrostatic stress can promote crack propagation and lead to brittle fracture. Materials such as ceramics, concrete, and rock formations are all subject to hydrostatic stress. The Coulomb-Moore theorem, and by extension the modified Moore theorem, considers the sensitivity of failure to hydrostatic stress and accounts for the difference between compressive and tensile fracture strength. For the modified Moore failure theorem, failure occurs when we cross the envelope line as defined in the graphs. Note the different factor of safety lines, OA, OB, and OC. These are developed based on the values of the principal stresses. In 1993, in his book Mechanical Behavior of Materials, Engineering Methods for Deformation, Fracture, and Fatigue, Professor Norman E. Dowling of Virginia Polytechnic Institute provided his details on the modified Moore theory. The Dowling equations that he developed are shown on the slide here. To determine the modified Moore stress value, we need to calculate the 3 principal stresses followed by the 3 Dowling equations. Once we have all 6 values, we take the largest one and compare it to the ultimate compressive strength of the material in order to determine the factor of safety. That's it for this video. In the next video, we will consider a new topic, fracture mechanics.